Well, hello everyone, and welcome to IC32B. So I'm not going to go over the whole thing because you all had no problems with IC32. I'm just going to go over the part that's new, which is the confidence interval. But first I want to talk a little bit about the problem. So the problem is that a coffee shop took a random sample of 50 stores, and they're trying to say, hey, are we better or worse than the national average, which is 200 cups per day with a standard deviation of 30 cups? And when we graphed that, what we discovered is that they are better than the national average. The sample came out to 209.96. The national average is 200. But let's talk a little bit about this sample. Okay, so this was the sample, this is 209. So does that mean that we really are 209? And the answer is no, because there's always sampling error. You know, we might be 209, we might be a little bit less, we might be a little bit more. The confidence interval is going to tell us where we are on that. And so what we do to construct a confidence interval, it's all based upon alpha, and alpha in all our problems is 5%. And then we're going to go ahead and calculate these, you know, the two-tailed, one-tailed, stuff like that. And because this one is a z-test, it's going to be norm.s.inverse of that probability. And then we can copy that across. And the reason these last two don't come out right is because it's the right tail. So inside here for the probability, we can't give it the 5%. We got to give it the 95%. So we just put 1 minus. Oops, I messed that up. Let me try that again. In front of the K there, I'm going to put 1 minus there. Now I can copy that one across. All right. Then for the confidence interval, we need the sample mean, which we've already calculated up above. It's this number here, which is the same as that number there. And now to get the lower bound of the confidence interval, we take that number, the sample mean, and we subtract from it the two-tailed right. So we're kind of going in reverse. We're using this to get a confidence interval. Take that number times the standard error, which is this number here. And that gives us the lower bound. And then we're going to take that same number plus this number times the standard error. And what that did is it created these two green lines. And if you look at these two green lines, what you can see here is that we know we're better than the national average of 200, but we're not sure that we're 209 better. How much better are we? Well, we're at least 0.94 better, because that's the lower bound. And we could be as good as 217 better. And you might be thinking, wow, that's a really big range. You know, I mean, can't we get more precise? And the answer is yes, we could get more precise, but the only way to do it will be to change our sample size. So let's say instead of 50, I put 500. I'm going to undo this. But if I put 500, you can see that the two green lines got much closer to our 209 and much further away from the 200, right? So in fact, it looks like that one is like 206. And now we know if 500 is the sample size, we know we're at least 6 better. And it looks like we could be as much as 211.89 or, you know, almost 12 better, right? But our sample size is too small to make a strong conclusion like that. So all we're saying is, yeah, we're better. We might be just a little bit better. We might be a lot better. We need a bigger sample in order to know just how much better. But for sure, we're better. Okay, so that's this one. Then in the next one, the batteries, the difference here is you're still going to put 5%, but this is a t-test, so this is going to be t dot inverse. And it's also going to insist that you lock this term here, which is the degrees of freedom. And the degrees of freedom is always the sample size minus 1. So you do that and then copy it across, and you'll have to do the same thing over here. For the right tail portion, you got to do the 1 minus the the probability or the alpha in order for it to come out right. Then this part is identical. So you get the sample mean from above, right? Just equals the number above. And then for these guys, you take that sample mean and you subtract, there it is again, the two-tailed right times the standard error, which is up here, same position that it was before. And then on the other end, you add the standard error. And now this was a different kind of problem because our CEO was claiming that the watch got 48 hours of battery life. We suspected that it didn't. And based upon running this test, we know for sure that it didn't, right? Because we're out here in the rejection region, right? So we know for sure we're not getting 48 hours. We're getting less than 48 hours. How much less? Well, our sample came to 46 hours, but we're probably not exactly 46 hours for the true population mean because there's always a range. What's the range? The range is 47 to 45.72. So in other words, we can tell our CEO, look, stop saying we're getting 48 hours. We're not. The best you can say that we might be getting is 47 hours. And it might not be that good. We might be as low as 45.72 hours. So, but for sure you can't say 48 hours anymore because there's no way that that's true based upon this sample. If we wanted to know just how good we are, well, again, we'd have to increase the sample size. This was only a sample of 25. Let's say I make that 100, right? And now, well, actually, that sort of works out even worse for us because now we know that, like, wow, we're not even 47. We're less than that. But obviously, with a bigger sample, this could also move the other way. So you just don't know. And that's it for the confidence intervals. So the confidence intervals are really useful. They're more useful if you have a larger sample size than what we typically have in these problems. But and they're particularly useful when you reject the null hypothesis, which in both these cases we're rejecting because we're way out here in the tail. Why are we out here in the tail? Because this blue line represents all the million possible samples that you could have gotten from the population. And what you'd expect is that your sample is going to be out here somewhere in the middle. And it wasn't. It was way out here. And so way out here means you reject the null hypothesis. And we'll see more about rejecting null hypothesis in lessons which are coming up shortly, where we will sort of explicitly do that by name. Okay, I hope this helps with the assignment. And we'll see you in our next class.